All right, worksheet 1225, AB number 11. You should try these problems, have tried them already. You guys should be getting pretty good at this stuff. Check your answers, and now here's an opportunity to see how these work out. So, some basic integration practice. It's going to be 4x to the 4th over 4 minus 6x plus c. Of course, don't forget that. That's kind of an easy one to start off with here. I don't think we really want to do like quotient rule or whatever on that. It'd be easier to simplify this. Sometimes you want to simplify things before you start integrating. So we could distribute the division. We are allowed to do that. And then this would be x squared over 2 plus 2x plus 6 natural log of the absolute value of x. You need the absolute values plus c. Don't forget the plus c. Second derivative, and the line is tangent to f of x. Okay, so we have a tangent line to the original curve, and we want to find the original curve. Now, we're starting with the second derivative, so we have to integrate backwards twice, undo the derivative twice to get to the original function. So the first derivative equals the integral of the second derivative, which is the integral of cosine x, which is going to be sine x plus c. Now, we need to find the c value, which means we need an initial condition for the derivative, which we have, because right here, this is a line, right? And its slope is -1, which means that's going to be equal to the slope of the graph at pi over 2 of the tangent line. Right? The tangent line has the same slope as the curve does. So we're going to use that. We're going to say, all right, well, let's plug pi over 2 in. And set it equal to -1. Sine of pi over 2 is 1. So c equals -2. So f prime of x equals sine x minus 2. So we're halfway there. So now we got to do it again. The original function is going to equal the integral of the derivative, which is the integral of sine x minus 2, which is going to give you negative cosine x minus 2x plus c. This is a different c value. So we need another initial condition. So at the tangent line, we'll also share the same xy pair as the function does at the point tangency. So if we plug pi over 2 in to this function, we get 0. So the point pi over 2, 0 is on the tangent line, is also on the function. So that's our initial condition. Plug pi over 2 in. It should equal 0. Cosine pi over 2 is 0. So c equals pi, positive pi. So your final answer, f of x equals negative cosine x minus 2x plus pi. All right. Little practice there. Let's see, f equals fb plus the integral of a to b f prime x, true or false. So this kind of looks like a fundamental theorem of calculus, but usually I don't memorize it like that. I think of it like this. I say, okay, well, if we're going to go to a to b like this, then that would be f of b minus f of a, right? Fundamental theorem of calculus, part 1. And then if you want to get f of a by itself, you'd have to add it over here and subtract that. So it'd have to be f of a equals f of b minus a to b of f prime of x dx. So this needs to be a minus So it's false. Number 5, looks like a little bit of properties of integrals. Definite integrals. They give you 8 to 2 is -3, 2 to 7 is 2 to 10 is 7, and they want 10 to 8. So remember, we could add these together, and if the bottom limit matches the top limit, you'll get a new one connecting the other two limits. So this is going to equal -3 plus 7 is 4. Now, be careful, because we want 10 to 8, which is the upside down version of this. So that means 10 to 8 is going to equal the same thing, but you got to change the sign. Okay. Here's another one. I would split this up. I'd bring the 3 out in front, f of x dx, plus integrate the 6. The 6 is inside the integral. And so we can integrate these terms separately. We usually do in our head and just writing them out like this. Now 2 to 7, they told us was 4. So that's going to be 12. This we actually have to integrate. You could either do the antiderivative, or you could be like, well, it's just a horizontal line from 2 to 7, the horizontal line with a height of 6. That's just a rectangle. It's 5 times 6 is 30. We're going to get the same thing here. We're going to get 30 here also, because that's 42 minus 12 is 30. So the answer is 42. Got some integration practice. Substitution, U-Substitution. Usually we shoot for what's inside another function clearly. Sometimes there's multiple things inside functions, so you try one, doesn't work, try a different one. And then sometimes you gotta get creative and do some weird, funky rules that we don't use a whole lot. So u equals x cubed plus 3, d equals 3x squared. I don't want the 3, but the x squared dx works perfectly. So this is going to be 1/3 integral of square root of u du. Well, that's 1/3 u to the 1/2 du. It's a power rule. It's 1/3 u to the 3/2 divided by the new exponent plus c. And then we got to rewrite it back in terms of the original variables. X cubed plus 3 goes in for the u. Don't forget your plus c. Number 8. Now, I'm going to go for this whole thing be my u. You could do the 2x, but that's a really minor U-substitution issue, and there's obviously more issues than that. So I think if we go cosine 2x, du equals -2 sine 2x. Got a little chain rule there. We want sine x 2x dx, but we don't want the -2. So this is going to be -1/2 integral of du over the square root of u, which is -1/2 integral of u to the -1/2 du. It's not natural log, power rule. So it's going to be -1/2 u to the positive 1/2 divided by the new exponent plus c. And that's going to be negative square root of cosine 2x plus c for your final answer. Let's see, number 12, you could try, at number 12, you might be tempted to think, oh, that looks like, inverse tangent or something weird. Well, okay, if it is, that's fine, but maybe try something simpler first, where we just make the whole denominator the u like we usually do, and we get 8 e the 2x dx. This is what we're doing. So this is 1/8 du over u, which is 1/8 natural log the absolute value of u plus c, which is 1/8 natural log the absolute value of 1 plus 4 e to the 2x plus c. And then, since the inside of this is always going to be positive, a little simpler answer is to write it without the absolute values and with parentheses instead. We still need some grouping symbols. But that's something I would always have you guys do, because For e to the 2x is always some positive number for sure. Plus 1 is always positive. So the absolute values, we can rewrite them without it. 13, we could go u equals 1 minus 4x squared. Du equals negative 8x dx. Perfect. Divide by the negative 8. So we get negative 1/8 du over the square root of u. Negative 1/8. Integral of u to the negative 1/2 du equals negative 1/8 u to the 1/2 divided by the new exponent plus c equals negative 1/4 square root of 1 minus 4x squared plus c. Next one, we could try u equals 1 plus x to the 8th, du equals 8x to the 7th dx, and that doesn't work. That's bad, because we need an x cubed dx, and we get x to the 7th. So this is where we get a little more creative, like, well, maybe it's inverse tangent, right? Inverse tangent has like something squared right there. So this is what I usually do. I write that, and it has to have a 1 plus here. And if that's not 1 yet, it has a different number, we got to factor that out first. You say, what would you put in here to get x to the 8th? Be x to the 4th. So that's going to be my u. And you should hopefully recognize that that's a better option, because that gives you the x cubed dx. Now, I'm going to say I don't want the 4. I'm going to say let's bring the 2 out in front. And then we have a 1/4. And then we have a du over 1 plus u squared. So this is 1/2 inverse tangent of u plus c. So this is 1/2 inverse tangent of x to the 4th plus c. So that was one of those more weird ones, but I tried the regular stuff first. Oh, this is a definite integral, by the way. So we're not done yet. You gotta do 0 to 1. So no plus c. So it's gonna be 1/2 inverse tangent of, if you plug 1 in, it's gonna be 1 minus 1/2 inverse tangent of 0. Now, inverse means we're saying what angle would you plug in a tangent to give you this answer out? So in other words, what would you plug in a sine over cosine that would give you 1, right? Well, what angle would you plug in sine over cosine that would give you the same answer for both of them? And that would be pi over 4 in quadrants 1 and quadrants 3. Quadrant 1, they're both positive. Quadrant 3, they're both negative, which gives you positive 1. Inverse tangents, assuming principal values. So we're going to go with the quadrant 1, pi over 4 minus 1/2. What would you plug in this tangent to give you 0? Well, what would you plug in a sine over cosine to give you 0? Essentially, what would you plug in a sine to give you 0? 0. So the final answer is pi over 8. Got to be good at your trig. Definitely not a trig in the AP test. All right. This one. Now, this one, hopefully you recognize that we could rewrite this first, simplify it. Now, we're going to need U-substitution for this guy, but not this guy. This guy, we should just integrate on its own. Right? It's a simple power rule. This one, though, we're going to need to use U-substitution. So don't, just because you need U-substitution for one term, don't force yourself to apply it to all the terms, because that's generally a lot harder to do and people really mess it up. U equals square root of x, du equals, so that's the same as x to the 1/2, 1/2 x to the negative 1/2 dx, which is the same thing as 1/2 times 1 over the square root of x dx, which works perfect for that. You don't want the 1/2. So this is going to be 2 integral of cosine u du. So that's going to be 2 sine u plus c. So that's going to be 2 sine square root of x plus c. So only apply U-substitution to what you have to. So that was just some good basic practice. And I got a few more response problems here for you to try. So try those if you haven't yet. Let's see. I think we had just done this problem on a recent assignment. Let's see. 12. Maybe? No. Just kidding. Okay. So, slope field, differential equation. Yeah, we just did this on a recent one. It wasn't, I forget which, some, but yeah, we could do it. Should be good at it then, I guess. Slope field, where does it equal 0? When x equals 0, that's here, 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 and here. There should be 12 points when we're done. Also when y equals 2, so here, here. We can plug 1, 0 in. We get 1 times -2, so -2 slope. Plug 1, 1 in, and we get -1. Plug 1, 3 in, we get +1. Plug -1, 0 in, get -2. I like to use these dots to line up to get the slope right. -1, 1. So -1 for the x gets raised to 4th is positive. So this can be -1. So it looks like we're getting the same slopes here as we're over here. So I wonder if this one's going to be a +1. -1, 3. Yep, +1. So 1 point for the 0 slopes, 1 point for the non-zero slopes. B says, while the slope field is only drawn at 12 points, it's defined at every point in the xy plane. Describe all the points in the xy plane for which the slopes are negative. So best, I don't know, I think the most algebraic, less guessy way of doing this is to take your differential equation, which is slope, and make it negative. And realize that this is always positive, except for when x cannot be 0, because then that's going to make the whole thing go to 0, which isn't negative. So really, it's the y minus 2 that needs to make this whole thing go negative. So y has to be less than 2. So you could say y is less than 2 and x cannot equal 0 as a description of all the points. Or you could describe it a little more visually and say all the points below the horizontal line y equals 2, but not on the y axis. That's describing the same thing, but in a little more descriptive way, thinking of a graph. C, find the particular solution. You guys should be getting really good at solving differential equations with initial conditions, finding particular solutions. So you got to separate the variables. By the way, this was probably worth 1 point. Part B, so it's probably 6 points for part C. It's a lot of points. And so we got to separate the variables. That's a point. If you don't do it, 0 out of 6 points. Okay, integrate both sides. Natural log of the absolute value of y minus 2 is x to the fifth over 5 plus c. That's 3 points right there. 1 point, 1 point, 1 point. If you don't put plus c, you lose the rest of the points. We should find the plus c. So we're going to plug a 0 in for the y, 0 in for the x, solve for c. So c is going to equal natural log of 2. That's a point. We're going to plug it back in. And we're going to try to solve for y. So we have to exponentiate both sides. You need the absolute values there. Now we can use rules of exponents and break this up, which will result in a nice, more simplified answer. It has to be multiplication. You gotta use rules of exponents from Algebra 1. The natural log of 2 is 2, but it's multiplication. To get rid of the absolute values, you're going to do plus or minus. We should pick the plus or the minus right now. If I plug 0 in, I get either 0 is 1 times 2 is 2. If I plug a 0 in over here, I get negative 2. So I need the negative 2 to make that solution make sense. It's the negative. I'm going to add 2 to both sides. And of course, we always need to include the domain on these kinds of problems, these free response solutions to differential equations. And there's two issues. There's here, are there any values of x that cause that to be undefined, division by 0, even root of a negative, natural log of a negative or 0? Nope, nothing there. And then we also need to look up here at the original derivative and see if the derivative is ever undefined. So the function can be defined. Generally, the function can have points in its domain that are like corners and things like that. But for these problems, we got to break it up at those points and give a single open interval. So there are no issues anywhere. So a single open interval is the whole interval of real numbers. That's a point. But you got to give the domain. All right, here's another one. Just to get you really good at this. So consider a differential equation. Y equals fx be a particular solution to this differential equation with initial condition f negative 1, 2. On the axis provided, sketch slope field at 12 points. So I'm going to look for 0 slopes first. That's going to be when x equals 0, which is here, here, and here. It's also going to be when y equals 0, which is here, here, and here. So we just got 6 out of 12 points real quick. And that's probably worth a point right there. It's probably 2, 1, 6. So 1 point for all the 0 slopes. We got to just plug in some things. There might be some symmetry here to help us feel more comfortable with our answers. 1, 1 is going to be negative 1/2. So that's down 1 over 2. So it'd be like connecting these points right here. And then try this one, negative 1, 1. If you plug negative 1 in for x, it makes it positive 1. So it's positive 1/2, up 1 over 2. So you kind of see the symmetry here. I bet these are kind of the same, but different signs. 1, 2. The 2 is the y value, which gets squared, becomes 4. So it's going to be negative 2, down 2 over 1. I bet this one's going to be positive 2. Just maybe double check it. Negative 1, 2, the x is negative 1 becomes positive 1. The y is positive 2 squared is 4. Positive 4 over 2 is 2. These are probably going to, look like they kind of flow into these better also. 2, 1, 2 for the x, 1 for the y. That's going to be negative 1. And then 2, 2 is going to be negative 8 over 2 is negative 4. So even steeper than that graph. So 1 point for all the non-zero slopes. Usually it should kind of stand out to you if you've messed up one of them. B says to write the equation of the tangent line to the graph. at x equals -1. Well, you need two things. You need a point and a slope. Now they gave us f of -1 equals 2 at the beginning, so you can't forget that. Sometimes they give you information earlier in the problem, and then you need it later on in the problem. They don't really mention that to you. So we have a point, we need a slope. So the slope is going to be dy dx at -1, 2. So -1 for the x, 2 for the y. That's going to be +2 is your slope. Sometimes that would be worth a point on its own. And then your final equation for your tangent line, y minus 2 equals 2 times x plus 1. And just leave it in point slope form. Just leave it in point slope form. All right. C, find the solution to the differential equation. So I'm going to just rewrite this right here so it's nice and convenient. And they also gave you initial condition. That's how we're going to find a particular solution. Otherwise, we'd be finding like a general solution or non-particular solution if they didn't give us initial condition to find the C value. Our answer would have like a C in it still. So we got to separate the variables. I would leave generally everything else on the right side as much as possible, numbers and negatives and stuff like that. But just because we're going to try and get the y by itself eventually on the left, so the less stuff I bring to the left right now, the less stuff I've got to move back to the right later on. This is, we're going to integrate both sides, so it's 1 point for separating the variables, but 0 out of 6 for the rest of the points if you fail to do this for some reason. This is y to the -2. This is power rule. Bump it up 1, divide by the new exponent. Over here, this is power rule, x squared over 2 plus c. So 1 point, 1 point usually. 1 point for writing the plus c. If you don't write the plus c, you lose all the rest of the points. I'm going to rewrite this a little more friendly. And then I'm going to use the initial condition, 2n for the y, -1n for the x, plus c. So it's going to be -1/2 equals -1/4 plus c. So least common denominators. I'm going to add 1/4 to -2/4. So we can get c equals -1/4. Or hold on, did I make a mistake? No, I think we're good. Okay, so that's another point. I'm going to plug it back in. And then we're going to try and solve for y. Now, I want to use this trick from Algebra 1 where I can flip the fractions on both sides of an equal sign. But it's got to be one fraction. So we got to think of this now. And this one's pretty convenient because you can already see them having these common denominators. And then you could flip them. Get rid of the negative. We could also write this a little nicer and just write this positive 4 for positive x squared plus 1. You could divide negative out of the top and bottom. Now that's your solution. You still need to figure out the domain. And so you look here and say, well, I don't want division by 0, so let's set the denominator equal to 0 and solve it. These are imaginary, so they don't affect our domain. Okay, so I don't need those. Any issues up here with original derivative x and y values that cause division by 0 or anything like that? Nope. So the domain is nicely, easily all reals, but watch out. Sometimes it won't be. So the last is a point, but you need this. You need the domain with the solution of the differential equation. And last problem, another related rates problem with a cone, the infamous cones. I don't know if you guys remember the trick for cones, similar triangles, to get the equation into purely R or purely H. So container has the shape of an open right circular cone. Show the figure. The height of the container is 10 centimeters. the diameter is 10 centimeters, which means its radius is 5 centimeters at the base, which is at the top this time. Water in the container is evaporating so that the depth, so water is leaving the top, evaporating at a constant rate of 0.3 centimeters per hour. So the depth is changing that, like that. So the depth is right here. So you have that. So we have a right triangle here, and then we have another right triangle here. And they together are similar triangles. The volume of a cone of height h and radius r. So they're giving you the volume of the cone formula, which is a little hard to remember. Cylinders are easy. Cones, spheres are tougher. And it says to find the volume of the water when h is 5 centimeters. So indicate units of measure. So we're going to need to figure out the r, though. So right away, we want to take advantage of these similar triangles. All right, we could say r over h equals 5 over 10, or 1/2. And so then we could, from here, say that r equals 1/2 h, or we could say h equals 2r. To get this in purely terms of one variable. Now, the fact that they gave you dh dt, right, this is dh dt, the fact that they're giving you h now means we probably want all h's. So we're going to replace all the r's in terms of h. So 1/3 pi 1/2 h squared. Now that the 1/2 gets squared also. So volume equals pi over 12h cubed. That's our new volume formula. And just by doing that, you get a point. You also get a point for writing r equals 1/2 h, so using your similar triangles. This is all stuff you want to do just to make this problem easier. I mean, you're going to have to use that fact at some point. Using it at the beginning saves you tons of work. makes things way easier. Now we can use this to find the volume on part A. I'm going to use it a lot for other parts. So it's going to be 125 pi over 12. And the units, I said use the units, are cubic centimeters. It's volume. B says, find the rate of change of the volume of the water in the container. So we're looking for dV dt when h equals 5. Indicate units of measure. So to find dV dt, they gave us dH dt, so we got to figure out, well, what's the relationship between V and H? Well, we already have it, right? Then we're going to take derivative of it implicitly with respect to time. Don't forget the dH dt, which you should be kind of worried about if you don't have dH dt, because they gave that to you. It's not relay rates if there's not more than one rate. So this is what we want. So this is going to be pi over 4. The height is 5. dH dt was given to us, and it was -3/10 because the height's going down as the water evaporates. And so then that's going to be, we could take away one of these 5s, and so then that would be -15 pi over 8. And the units are volume, cubic centimeters, over time, which in this problem is hours. And it's negative. Do we expect that the volume is decreasing as the water evaporates out? Yes. The sign makes sense. Alternatively, this is just to illustrate real quick why you really want to do this. This is the much easier way, because if you did volume equals 1/3 pi r squared h, then dV dt would be 1/3 pi r squared dH dt plus, you have to do product rule, right? Plus h times 1/3 pi 2r dr dt. right? And then you have this and you have this, but now you got to figure out what the R's are and what the dRdt is. And you're going to have to use that special relationship up there. You're going to have to say, oh, well, R over H equals 5 over 10 equals 1/2. So R equals 1/2 H. So R equals 1/2 10 is 5. And then you're going to say, well, dRdt equals 1/2 dH dt. So that's going to be 1/2 of -3/10. So that's going to be -3/20. And you're going to plug those into this and then get that same answer. Well, please don't do that. It works. You can do it. You're using you still haven't used the similar triangles. C, show that the rate change of the volume of the water in the container due to evaporation is directly proportional to the exposed surface area of the water. Let's try and interpret that in a short mathematical expression. Show that the rate change of the volume of the water in the container due to evaporation, that's dV/dt, is directly proportional to the exposed surface area of the water. And then they want to know what the constant proportionality is, which is what we usually use K for. You can use any constant. Directly proportional means times the same value all the time. It's like a linear kind of relationship. So that's what they're saying. So that probably, now surface area is pi r squared. So we probably want to get an answer that has like pi r squared in it. So there's two ways of doing this. My idea is let's rewrite the volume formula, the 1/3 pi r squared h, so that has all r's instead of all h's. And so I wrote it earlier that h equals 2r was one option. And so then we get 2 pi over 3r cubed is a nicer, more friendly possible way of getting a pi r squared in our answer. So now if I take the derivative of this implicitly with respect to time, I get 2 pi r squared dr dt. And look, there's our pi r squared. And we got to figure out dr dt. So we have to use the fact that r equals 1/2 h. So dr dt equals 1/2 dH dt. I was just showing you this on the bad way of doing the last problem. And dH dt is -3/10. So dr dt is -3/20. So I'm going to plug those in there. So we get -3/10 pi r squared. So that shows that the rate of change of the volume of the water in the container due to evaporation is directly proportional to the exposed surface area of the water. The constant of proportionality is that guy. So that was kind of a weird question at the end. It was worth 2 points total. So if you're like, oh my goodness, I don't know what it means. Okay, you can still get a 5 with the 7 out of 9 on. If you average 7 out of 9, that's easily on track for a 5. 5 points for part B, 1 point for part A. But then you got a point for this and a point for this. Those are some of the points from part B. And then you got a point for taking the derivative. You got 2 points for taking the derivative implicitly. And then you got another point for your final answer. And on this one, you got a point for this, and you got a point for this. So, good stuff.